Hello everyone and welcome to this Basic Machining Center programming webinar sponsored by Hartwig. My name is Joe Million. I'm one of the application engineers here at Hartwig. I'm being joined behind the scenes today by Ricky Hochecker, who is helping me answer any questions that we may have. There is a chat box that you guys can type questions in should you have any. Ricky will be able to review those questions and he will either read them whenever I pause to ask for questions or answer directly to you. Here at Hartwig, we help people in manufacturing control their destiny every day, and it's our hopes that this webinar will help our customers and some of their employees new to machining centers learn how to program them. Let's get started. First off, what is G-code? G-code is a programming language used to provide a list of instructions to computerized machine tools. Okuma uses a .min file extension to read ASCII texts. These files are generally read line by line from top to bottom. Each line is referred to as a block in technical terms, and blocks may contain various codes known formally as words. G-codes, which is what G-codes are named for, would typically be followed or be associated with an axis address that we would tell the machine to move to that point. M-codes would typically be used to turn a machine component on or off, be it a spindle, an actuator, or perhaps coolant. Our first and most basic G-code, or the one that we might use most frequently, is G0 or G00, and that's for rapid traverse. G0 will stay on until it's told to stay off. But let's go into a couple of tangents about G0 while we're on our first G-code. The first thing is whenever we're programming in G00, our machine might not actually move in a straight line. If I have my start point, like I see on this graph here of x of 2 and 2, and I have an endpoint of say x15 and y6, and I command that with a G00, my path may move more along this red line than along that light blue dotted line, which would represent the linear path. This is normal as the machine tries to accelerate each axis as quickly as it possibly can whenever it's in a G00 move. Another thing we need to consider about our G-codes whenever we get into them really early is whether our codes are modal or one-shot codes. Modal codes will stay on until they're overwritten by another code, and a one-shot code is valid only for the line that it's on. Another thing that I'd like to point out real quick is that we can use G0 and G00 interchangeably, and the same thing for G01 and G1 and M01 and M1 and all of the G's and M's that are less than 10. We prefer to use the two-digit G00 or G01, especially because whenever we go to edit programs, it makes it easier to edit programs if we use G01 versus G1. And you can see here I'm trying to find a G1 in my program, and my find tool picked up a G15 instead of the G1 that I wanted to find. If I was to have used a G0 in my program and searched for G01 instead, I would have only arrived at the G01 right here. So that's a styling preference. That's not a rule. So going over some more basic G codes, we'll have G00, which I already covered. We have G1 or G01, which we'll use to do a linear interpolation. A G01 will never do that dogleg motion we talked about earlier, but a G01 also must have a feed move associated or a feed rate associated with it for the machine to know how fast to move the axes that are commanded. We have a G2 and a G3, which we can use for circular interpolation and counterclockwise circular interpolation. We have a G15, which we'll use to select which work coordinate system we want to be in. We will use, in the course of this webinar, only G17 for XY plane selection. There is an XZ and YZ plane selection, but it's beyond the scope of this course. We have a G20 and G21 code for checking whether we are in inch or metric. That's very handy to make sure that you're programming in the system unit that you thought you were programming in. We will use a G56 to do tool length offsets in the Z-axis. We will also use G90 and G91 to decide whether we're going to be in absolute or incremental mode. for our positioning, and G94 and G95 to see whether we're going to be in feed per minute mode for our feed rate. Some of the basic M codes we have that we'll use early in this class are M0 and M00. Both of those mean the exact same thing, and they bring the machine to a stop. That'll usually stop the spindle, stop the coolant, stop everything else, and let you open up the doors and look at the part that's inside. Although some machines may be configured slightly different, and they may leave the spindle on, or that depends on machine configuration. M1 and M01 works much like M00, except it only stops the machine when the optional stop button on the control panel is illuminated. We have an M3, which is a command that we'll use to turn the spindle on clockwise, and an M4 would turn the spindle on counterclockwise. We'll use an M5 whenever we need to stop the spindle. We will do a few tool changes over the course of this class, and an M6 is the command that we use to make the tool changer operate. We'll use an M8 to turn on our main or flood coolant. An M9 turns off all of our coolant, whether they were the main coolant or not. And an M2 and an M30 both mean the same thing, and they are the end of our program. Some other common words that we're going to encounter over the course of this webinar include the sequence name or line number, which starts with N. Anytime you use a sequence name or a line number, you're going to want to put that at the beginning of the line of code. If you try to put an N anywhere in the middle of the code, or anywhere in the middle of the line of code, you're going to get an alarm. Another code that you would typically see only at the beginning of the program would be O. It wouldn't be too uncommon to see a program that had O and then 4 characters after it that would represent the program name. If we're using subprograms, that's how we tell the controller which subprogram name we want to target. We will use an S whenever we need to command spindle speeds. We will use an F whenever we need to command feed rates. We will use an H value typically whenever we need to specify an offset number, be it a tool offset number or work offset number. We will use a T to specify tool numbers. And we will use V whenever we're talking about something that concerns a system variable. And we'll go over system variables only very briefly later on in the webinar. Our first programming example, we're going to use primarily fixed cycles, and fixed cycles are pre-programmed cycles that'll take care of some of the work of programming the machine for you. Most of the fixed cycles are useful, or most of the fixed cycles that we're covering are used for hole creation. G81 and G82, for example, would be used for drilling a hole where you didn't have any PEC. We could use a G83 or a G73 for drilling a hole whenever we wanted to PEC. We have G84 and G74 that we can use for tapping or reverse tapping. We have G85 and G89, which work for boring. Both of those operations feed the boring tool out. We have a G86, which we would use for boring if we wanted to wrap it out. A G76 is a fine boring cycle, and that tool path will actually shift the cutter slightly away from the work before wrapping it out of the hole. We have a G87 cycle that can be used for back boring, and a G80 cycle, or G80 is not a cycle, G80 is used to cancel fixed cycles. And G00 can be used to cancel a fixed cycle and leave the spindle on. We'll get over that in a little more we'll get into that in a little more detail here in a moment. I will try to refer to them as fixed cycles. In a lot of other programming or a lot of other machine builders terminology, they would refer to these as canned cycles. Here is a video, or here is an animation of our first program that we're going to write running. The program just drills a couple of holes and then comes in and taps those 2 holes. Make things a little easier for everybody to understand, here is a blueprint, or a basic blueprint for this first little part that we're going to do. It's a simple 4x4 block with its origin in the center, and then we have 2 holes appearing an inch above the y-axis and an inch left and right of the x-axis. We're going to make improvements to this program as we proceed through this webinar, so do not take these first slides as the way that all of your program formatting should look. I figured it was better to do a few things good and then do a few things better, so we will make improvements as we go along. The first move of this program, we're going to go into rapid traverse mode, and then we're going to send the tool, or we're going to send the tool, actually, yes, to the top of the envelope in Z. Hopefully 50 inches is enough for us to get up there. Then these safety lines are pretty common whenever a lot of people program to put, or a lot of people commonly put these three codes at the top of their program. This says that we want to use absolute positioning mode, so all of the values in our program are going to be from our work coordinate system 0, not from our last position. We're going to use a G94, which means that we want to feed in inches per minute. And we're going to use a G17, which means we want to use the XY plane selection for the course of this program. The next line of this program says that T14 will be the next tool in this program and that we want to change to it now. That's followed by a switch into work coordinate system 1 with a rapid move to X-1 and XY1. Our G0 from above would still be active, so the machine would still be moving in a rapid traverse manner. After we position to our start point in X and Y, we want to move to our start point in Z. To do that, we will activate our tool length offset while we are rapiding to 100 thousandths above the work, and we are setting our spindle speed to be 3,500 RPM. We are not, if you will notice, turning on our spindle just yet. One of the things that we want to do whenever we're programming our tools and programming our tool numbers is we'll want to make sure that we match our tool number to our tool length offset number. We established our tool number with our tool number, but we almost always want our tool offset number to match our tool number. Otherwise, programming can get a little confusing. So now let's get a little deeper into work and length offsets. So our work coordinate systems, I mentioned we're going to use work coordinate system 1 for this first program. That is selected on your work coordinate system tab, or we can see that on our work coordinate system tab of the display. I have coordinate system 1 selected, and there are the positions of my work 0. On an older control, your work coordinate system display page will look a little more like this. And we are just using that G15 to select which row of this table that we would be selecting. Whenever we look at our tool data, we want to be careful that we make sure that we are looking at the left-hand side of the screen to see the information that's displayed on the right-hand side of the screen. So the tool that's selected on the left is displayed on the right. Here I've got tool 1 selected. You can see that by the blue box in the actual tool number box. And then that correlates to the tool length offset of 1, or the tool length offset 1 in the offset data table for tool number 1. But on that very same page, I could have tool number 14 selected. Here the blue is on tool number 14, and I've got tool number 14 displayed on the right half of the screen with the tool length offset for number 14 in the geometry box there. On an older control, this might be closer to what you see whenever you're displaying your tool length offsets. For the sake of this class and machines with less than 100 work offsets, we'll say that the tools 1 through 100 are the same on this display as they are on this display, or their length offset would be the same. The wear value that you see on this page may or may not be on your control. Newer controls, this is becoming a more standard, wear is becoming a more standard feature, but not every machine sold will have a wear column. So now we're going to get back into our fixed cycle for drilling. This fixed cycle command says that we are going to drill a hole at our current XY position to a location of Z negative 0.75 with a retract plane of 0.1 above the work and a feed of 50 inches per minute. Fixed cycles will turn the spindle on. So anytime we're using a fixed cycle, we do not specifically have to turn the spindle on and off ourselves. After it's finished drilling that hole, it'll move to X of 1, and it'll drill another hole with the exact same parameters as the last one. At this G80 line, that'll be the end of the cycle. And then fixed cycles will also turn the spindle off whenever they're done. After that, we'll wrap it back to the top of the work envelope. We'll change to tool 16. We'll wrap it back over to X -1, Y1. And as a point of note, on an Okuma control, we do not need a decimal place in our figures. Y -1 and Y -1.0 will get you to the exact same number, or to the exact same position. This next line, the G56, is our tool length offset. We're going to call tool length offset 16. That's a typo in my little bubble note there. And we will move to a Z of 0.1 at an S of 1,000 inches a minute. We will then have a fixed tapping cycle where we're going to tap a hole at the XY location of the XY location we're at to a depth of -0.75. So hopefully that was only a 1/2 inch plate that we drilled through. Otherwise we bust a tap at the bottom of the hole. We're going to have a retract plane of 0.1, and we'll have a feed of 41.66 inches per minute. Now that feed number to me is a little goofy, and we'll go over that in a minute. But to figure out that feed rate, I took 1 divided by the threads per inch in the tap, and I multiplied that by the RPM that I'm spinning at the moment. After it taps that first hole, the machine will move over to an X of 1 and tap another hole with the same parameters as the last one. At the G80, it'll be the end of the fixed cycle. We're going to wrap it to the top of the envelope in Z, and then we'll end our program. So if we watch here, here's that program running again after having that explanation of everything that it's doing. Are there any questions so far?
No questions so far, Joe.
On our last program, or program example, we did cover tapping. One of the things I would like to point out with newer machines especially, synchronized tapping is a standard option. Older machines, that's not the case, but with newer machines, synchronized tapping has become a standardized option. And if you have synchronized tapping available on your machine, you most likely want to be synchronized tapping all the time. We can use a synchronized tapping cycle if you have a float tap holder, but you cannot use a float tap cycle on a rigid tap setup, or you're going to have problems with taps pulling out or breaking. So we would prefer, if you never plan on using a float tap, and a lot of shops don't even have float tap holders anymore, that you would switch your machine over to synchronized tapping. We also went over the fixed cycles briefly, and there is a page of parameters that we can change or tweak some of the retraction levels or retraction directions of some of those fixed cycles on. And then we also have some things that happen at M2 and M30 that I think are worth mentioning. Whenever we hit an M2 or we hit an M30 or we hit reset on the control, by default, newer machines are going to go into G00 mode. They're going to select the G17 work selection mode. They're going to cancel the tool length offset. They're going to go into absolute mode. They're going to go into feed per minute mode, and they're going to turn their stroke limit off. This is the default settings of the machine. Those can be configured if you want to configure them differently, but knowing that that happens every time that you hit reset or an M2 can allow you some flexibility or some shorthand in your programming that might be desired by some. So now we've got a slightly revised version of this program, and let's go over the differences that we made to this. This program would perform the exact same way, but I think it's easier to read and maybe more stylistically correct. Programming is much an art. There are things that are style that don't really affect the way the machine runs, but may affect the way that other people can read the code and interpret what the code is going to do. The first thing we did to this program to change, the first major change we did to this program is we included a G20 in one of the very early lines. This G20 line simply ensures that the machine is in inch mode. We want to make sure that the machine is in the mode we're programming in, because on our very next line, we get a good example of this. We're feeding to a Z of 500 inches. So if I was not checking if I was in inch mode, and I was using just a Z of 50 like I did on that earlier program, if I thought I was in inch mode and I was actually in metric mode, my first G00 line would be to a distance of 50 millimeters. And 50 millimeters is not a very big distance. That would probably be into the work after I canceled my tool length offset, not up to the top of the envelope. So not only does the G20 make sure that I am in inch mode, the 500 is a more reasonable number because most Okumas would make it to the top of their work envelope in 500 millimeters even. Another thing we're going to do to this program to make it easier to read is we're going to add comments. Nothing inside of a parenthesis is read by the machine outside of a second parenthesis, so don't put parentheses inside of parentheses. But nothing inside of a parenthesis aside from that is read by the machine. So anything in there is just to make things easier for the people running it to see. We like to include a tool list with a brief description of what that tool does towards the top of the program. And then as we call each tool, we like to say what that tool is actually physically is. Another thing we like to do is we like to put line numbers above each tool to help with restarting. It's my preference to have an N that matches the tool number, although you could have that be the order of operations of your program. Line numbers do not have to be in sequence, so we don't have to start at 1 and increment in positive numbers. We can start at 100 and we can have our next one be 23 if we want. That'll work just fine. Again, I prefer to have them matching the tool number so I can find them easier in the program. Another thing that we're going to do to this program to make things a little more correct or a little less likely to run into hiccups is I'm going to set a G90. So I'm going to say I want to be in absolute positioning mode, and I'm going to set my G15H value after every time I do a tool change. And the reason we put this G90 and this G15H line after every time we do a tool change back in the program is it would be possible to have more than one part ran by each tool. I could have 15 parts on a table, and I want to get my tool and I want to run that tool on part 1, then I want to run that tool on part 2, then I want to run that same tool on part 3, and so on and so forth. Well, whenever I come back to my next tool, I need to make sure that I'm restarting at the correct workpiece. Another reason that it's good to put that G90 value in there is it's not uncommon for somebody to have a subprogram that runs in incremental mode. So I would position a tool to where I wanted it to be at the start of a tool path, then I would have a subprogram that moves everything inside of it incrementally. But if I was to hit reset, or if I was to forget to come back out of incremental mode whenever I go back into my program, I could have issues with my positions not being where I wanted them to if I was to stay in incremental mode whenever I wanted to be in absolute mode. So we just like that being there to make absolute sure we're in absolute mode. Another thing that we did differently in this rendition of the program is we're using G56HA instead of G56 to match our tool number. Anytime we use a G56 and we use an HA, we will get a tool length number that matches the tool number of the tool in the spindle. So if I come along and I change my program, I don't have to remember to change my H14 command on this G50, on that first G56 line per se. I could just change the tool number and the rest of the program would still work. It would automatically get the correct offset of the tool that's in the spindle. And here I can see a sample of that tool data screen. On the newer machines, they actually label the HA and the DA right there next to the tool 1. So I'm looking at my active tool number, and its HA and DA values are the same as its tool number value, which is 1. Another thing that we're going to do slightly different, or that we've done slightly different in this version of the program, is we're using a G94 whenever we go to run our drill, but we're using a G95 on our tap. And we want to command that G94 or G95 on the first feed move after every tool change, because it wouldn't be uncommon for one tool to use a different feed rate system than another tool. And another thing that I'd like to point out is that when we're tapping, it's my preference to be in feed per rev mode. The feed per minute that a tap is moving doesn't really mean much to me. I'm concerned about how many feed per revs it moves, and pretty much that only. So I will usually put my feed per rev mode like listed here, where that was a 3/8/24 tap. So my F will equal my 1 divided by my pitch, or 1 divided by my threads per inch, I should say. And here we see that program running. Although there are differences in the program, from our perspective as a program reader or writer, there's no differences in that program from the machine's perspective. Any questions so far?
Nothing so far.
All right, for our next example, we will be profiling around the outside of the same 4x4 block. This time we just won't be concerned with the holes, we'll be concerned with programming around the outside of the part. So if I look at my program here, all it's doing is going around the outside of the part. So looking at the program, the first thing I'm going to do is ensure my machine is in inch mode. The next thing I'm going to do, this is another way to send the tool to the top of the work envelope, is I'm going to use a system variable for this. So in the last one I mentioned that we might want to use 500 instead of 50, because 500 will get most machines to the top of the work envelope. This Z equals VPPLZ method that you see here will get every machine to the top of the work envelope every time. And it doesn't matter if you set your work offset to be 500 inches below your table and everything was programmed to positive 500 moves, you'll still get to the top of the work envelope every time whenever you use the G00 Z equals VPPLZ, regardless of work coordinate system, machine configuration, or anything. It's very common for me to program that command, usually first or second line in a program, and then at every tool retraction thereafter. I'm going to change to tool 1 in this program, which will be my first tool. It's a simple 1/2 inch 4-flute end mill. I'm going to activate my work offset 1, and I'm going to move to an X of -2, a Y of 2, and I'm going to use absolute positioning to do that while I make that move. I'm going to call my G56 HA for my tool length offset. This will call the tool length offset for tool 1 because that'll be in the spindle. I will set my spindle speed to 5,000 RPM, and this time, because I'm not going to be using a can cycle or a fixed cycle, I will use an M3 to turn the spindle on myself. The machine isn't going to do it for me. Outside of a fixed cycle, the programmer must turn on and off the spindle. So after I've brought the tool to the top of the work, I'm turning on the coolant. Now, this is another personal preference of mine. In a higher production atmosphere, you might want to kick your coolant on before you retract to the top of the work, because you might want your coolant flowing before your tool gets anywhere close to the part. I myself like seeing the tool get to the part before everything gets splashed with coolant and makes me unable to see what's going on. After that, we'll use a G1 to do a feed move to a Z of -1/2 inch. And we'll do that at a feed rate of 100 inches per minute. We'll then move to a Y of +2. That G1 and the F100 from the line above are still active. We'll move to a Y of -2, then an X of -2, then a Y of +2, then we'll move back up to our start point, 100 thousandths above our work. Then we'll rapid traverse to the top of our work envelope. Then we will end the program. And if we take a look at this program again, just goes around the outside of the block. Any questions so far?
Is there a G code that will force rigid tapping and it not be dependent on the parameter setting?
Yes, I forget the G value off the top of my head, but there is a G code that is, there is a G code for rigid tapping that's separate for synchronized tap, or that's separate from float tapping if you have both and you wish to use one or the other.
Yeah, I have it right here. G284 is for right hand tapping and G274 is for reverse tapping. I'll drop that in the chat.
Okay.
That's your only question.
Only question. All right. Well, hey, got a question. All right. Moving on. So now we're going to get into arcs, and this is our basic little training program for arcs. So you'll notice that whenever I start on this C here, I started on the lower corner of the C. Then I do an N, and then I'm starting on the top of the second C, would be the important thing to note. And then I'm going home. So here's a blueprint of my part. The design of it's, you know, the actual numbers are a little trivial, but the idea here is to get your head around using a G2 and G3 move. So one of the things that I'd like to point out is that we're going to be using circular interpolation, and there's two ways we can command our circular interpolation moves. One is to use an R command inside of our G2 line. With an R command, the thing to keep in mind is that there are up to 4 circles that could be drawn between any start point, any end point, and a radius. There could be no circles available, there could be 4 circles available. So we need to do a little more to define which circle it is we want. G2 and G3 gives us 2 of those circles and eliminates the other 2 because we'll want to know whether we want to move clockwise or counterclockwise. We then use a positive R for angles that are less than 180 degrees, and we use a negative R for angles that are greater than 180 degrees. So inside of our program that we'll look at here, the first intro lines of the program are still very much the same as the last program. We're checking that we're in inch mode. We're using that system variable to get to the top of the stroke. We're changing to tool 1, activating our work offset. We're using offset 10 this time, but it doesn't matter which offset we use as long as we set the correct offset. Then we're moving to our start point, which is not, you know, the same as the last start point, but your start point is going to be different on every program you have. We want to do that in absolute mode. We're activating our tool length offset, kicking our spindle on, kicking our coolant on, feeding down 100 thousandths below the work, because we're just doing a little engraving pass here. And now here's where things get a little bit different. We've got a G2. This is our first arc move we've commanded, and we're saying we want to move from the position we are in, which is x -16, y of 7.5, to an x of 4 and a y of 7.5. Our radius is 6 inches, and we want to make sure that we are in the G17 XY plane selection. And then whenever I get to the other side of the C, whenever I'm moving in the other direction, I would be using a counterclockwise arc. So that first time it's machining the C clockwise, that second time it's machining the C counterclockwise. Here I'm using a G3, and I want to move from my start position at X56, or my current position of X56, to a G3 of an X44 and a R of 6. If you are starting and stopping in the same position on an axis, you don't need to list that axis here. So in this case, my x-axis is changing, but my y-axis is staying the same. So I don't need to include my y in position on that line. It knows that it'll be the same. And then the other thing that I'm doing a little differently here is at the end of my program, I'm using a G30P15 to send the machine to a home position. I want to make sure that my operator has an easy time removing this plate after the cycle runs. So to use a home position, I must set one of those up first. Here, I've set up home position number 15. And then after you've set the position you want it to go to, you need to set the movement order that you wish it to move in, or else the cycle won't do anything. Here, I want my z-axis to move first, and then I want my x and my y-axis to move at the same time to their home position. And if we take a look at that program here, there we're feeding clockwise as we move around the circle. We're doing our in, which I kind of skipped over in our program because we're just doing straight lines. And now we're going to a counterclockwise C. And then the machine's going home. So next we're going to do the very same arc, but instead of using, or we're going to do the very same design, but instead of using I's and J's, or instead of using R's to command our radius values, we're going to use I's and J's. So I correlates with the x-axis, J correlates with the y-axis, and K correlates with the z-axis respectively. Whenever we program using I's and J's in this case, because we're only going to be using the x and the y-axes, we're going to use I and J to describe where the center point of our circle is in relation to our start point in incremental moves. So if we look at our first arc move there, we started at an x of positive 16, and then our arc has a center point that is an I of negative 6. So it's incrementally 6 inches negative in x from our start point. And the machine will then be able to do the math from our start point and where we're telling it the radius is to calculate accurately the arc. And here, again, we're moving in a clockwise arc from our current position to an x of 4 and a y of 7.5. The center of the arc in this case is a positive 6 inches from our current location in x. And then on the G3 side, it works the same way. Whenever the center of our circle is in a negative direction from our start point, we're going to use a negative 6 to describe our I. And it was the same thing for the very last edge there. So as we watch this animation one more time, and we come around the bottom of the C, now we come around the top of that first C. We do our in, which is just G1 moves. And then we go the other way around the second C to demonstrate some G3. Any questions so far?
Nothing about that.
Okay. So the final topic that we're going to cover today is cutter radius compensation. There are 4 main types of cutter radius compensation that are used. One of them is no cutter radius compensation, and that's what we've been doing so far. So in that program where we went around the outside of the block, that block was supposed to be 4 by 4, we messed up and it wound up undersized because we weren't using any cutter radius comp. Another very common version of cutter radius compensation that's used is what we'll call controller compensation. And in this form of compensation, you'll have the controller in charge of the compensation. We have a computer compensation, which will put the onus on the programmer to do the tool's compensation, and then we'll have a where compensation, which is kind of a mixed match of both. Let's look at these in a little more detail. So if I don't use any cutter compensation, the center line of my tool will follow the program path. If I'm profiling around the outside of the tool, this will cause the radius to gouge. But this is typically the way I program whenever I'm drilling holes, or whenever I'm facing a part, or whenever I'm doing something that doesn't require using the edge of the end mill. Here in this programming example, I've got cutter radius comp programmed with no comp. And if we look at the pink text here, that's what's going to be changing from program to program to program as we review these different types of cutter comp. You'll notice that my x -2, y -2 is the exact position of the start point and end point, and I'm just moving around the exact edges of the block. The next version of cutter radius compensation that we use we'll call cutter comp control. In this version, we're using the machine's tool data table, and we're using a G41 and 42 in the program to control the direction of our tool length offset. So in this version of cutter comp, the center line of the tool will be offset by the value defined in the tool's data table, and it'll be offset in the direction set by G41 or G42. And G41 and 42 are defined as left and right, and they're defined in that way. So if you were moving your cutter in a positive Y direction, a G41 would move to the left of your programmed line, and a G42 would move the cutter to the right of your programmed line. I prefer to think of these as G41 being climb milling and G42 being conventional milling. That's just easier for me to think about. One of the good things about this type of cutter comp is it allows for different size tools to be used. In some shops, they don't always have the exact size of the end mill that was specified by the programmer at the time it was programmed, and it's nice to be able to use the same program with different size tools. And here we have a cutter radius comp control. Here's what the data page would look like. So I have my HA and DA. I can use an HA and DA inside of a program with my G41 and G42, just like I can an HA and G56, and it'll get the geometry out of the appropriate spot. One thing that's important to note is this is my cutter radius. So in this example, I'm looking at a 1-inch end mill, and it's got a cutter radius compensation value of 1/2 inch. So let's look at the program example of cutter comp control. I can see that I've got my G15H1, my X -2, but I've got a lead in built into that -2.6 value. So on my last program, I was starting at an X of -2. On this program, I'm starting at an X of -2.6. I want to lead out, or I want to have a lead in and a lead out of a little more than my tool's radius. Otherwise, I'm going to have problems getting the tool started and stopped off the work without running into something that I didn't want to run into as cutter comp turns on and off. And then you'll notice the rest of my values as I come along the program are the same that they were in the other program. The X's are all still once cutter comp is turned on, the X is still 2, the Y is still 2. And then we have a lead out where we lead out a little more than half the tool's radius. And we use a G40 to cancel our cutter compensation. One of the problems that we can have whenever we're using cutter radius compensation is that you cannot have a big enough lead in. Here I'm going to charge this mistake to the programmer. He put a comment in there that this is a 1-inch radius end mill. Now the programmer meant that it was a 1-inch end mill with a radius bottom on the end of it. But what the night shift operator, whenever he grabbed the program, thought the programmer wanted was a 1-inch radius end mill or a 2-inch end mill. So that's what he put in the machine. And whenever he goes to run the program, he finds that it clips the corner of the part as it comes around, because there's not enough lead in and lead out to support a cutter so large. The next type of cutter compensation that we use pretty frequently is called computer comp. In this type of cutter comp, the radius of the tool will be compensated by the program. We don't use a G41 or G42. It requires the tool be the correct size or incorrect work size will result. And this is a pretty common strategy whenever you're using a CAM system. So if we look here, I'm doing the extra math myself to compensate for that cutter's path. I'm adding in the tool's radius and X and Y as I come around the part. So my X and Y values, instead of being nice and even 2s, are 2.5s because I have to do the extra math for my tool's radius. Some of the problems you'll have whenever you use this method, because there is no cutter compensation, if your cutter is too small, or if your cutter is too large, your part winds up being too big or too small. And there's nothing the operator can do about it if he doesn't have the correct size end mill. The final type of cutter comp that we'll talk about is cutter compensation wear. In this type of program, the radius of the tool will be compensated for in the program like it was in cutter comp computer, but we will also be turning on G41 and G42. This allows the tool size to differ from what's programmed, but we won't have such a large lead in and lead out because we don't have half the tool radius that we're trying to shift. We're maybe trying to shift what our grind stock amount was. And this type of tool offset is this type of tool wear offset or tool radius offset is really common in CAM systems. If we look at our example here, we can see I've got, instead of a negative 2.56 lead in like I did on the other like I did on the control version, I'm only feeding to negative 2.53 here, and you'll see there's almost no lead in showing on that animation at all. In fact, you can't even see the lead in because there's so little actual lead in by the time that's all moved around. Any questions so far?
Nothing.
Okay. Well, that brings us to the end of our presentation. We have an application support line here at the St. Louis office now, so if you'd like to reach somebody at the St. Louis office but you don't know who, you can reach us at our application support line at 314-684-4200, and when you call that number, every application engineer working out of the St. Louis office's desks rings. So if you leave a message at that number, we will all get a voicemail that you left that message. So the first available person will respond to you. If you think your question is more appropriately answered by email, you can email us at aesupportstl@hartwiginc.com. If you'd like to get a hold of either me or Ricky directly, our contact can be found at the end of this presentation. We'll be sending along a thank you package to those that intended that includes a few of the manuals that I pulled some of the information from today, and it'll include a questionnaire as to how we did on this presentation, and it'll include our contact information as well. Thank you very much.